The road to the periodic table began in ancient times, and after about 5,000 years, it took us all the way up to the 1700s and the birth of modern chemistry. And the birth of modern chemistry will take us through the 1700s and into the middle of the 1800s. The publication of The Skeptical Chemist turned us in the direction of what we know today as modern chemistry. Before the publication of Boyle's book, only 12 elements were known, and it took 5,000 years to discover those. Within 100 years of Boyle's death, another 20 would be discovered, and within one generation, a chemical revolution would be underway, a revolution that centered around the other father of modern chemistry. When he was only 5 years old, his mother died, leaving him parentless and very rich. His interests turned to chemistry, botany, and mathematics. He was the French chemist Antoine Lavoisier. It's even fun to say his name, Lavoisier. Lavoisier published his book, The Elements of Chemistry, written in French, of course, which, along with The Skeptical Chemist, totally changed the world of chemistry. Lavoisier named the elements of oxygen and hydrogen. He introduced the metric system, and he wrote the first extensive listing of elements that could not be broken down any further, the building blocks of nature and of chemistry. Like Boyle, Lavoisier established means to make chemistry a highly measurable science and to keep thoroughly accurate records in order to precisely track advancements or failures. For example, he would put his chemist assistant, Armand Ségine, in an airtight rubber suit with tubes attached around Ségine's mouth. In this way, Lavoisier could carefully measure the exact amount of water and carbon dioxide that Ségine exhaled using very precise scales. Plus, by carefully monitoring the experiment, Lavoisier ensured that he was never the one that actually had to get inside the rubber suit. Bonus. In another experiment, he and some colleagues purchased a raw diamond and then built a very impressive-looking apparatus. Using a gigantic magnifying lens, they used it to vaporize the diamond, which was enclosed in a container. Analyzing the gases produced, Lavoisier proved his suspicion that diamonds were actually made out of carbon, exactly the same as coal, but in a different form. Now, here is something particularly significant from his experiments. See if you can follow along. Lavoisier proved that the amount of weight you start off with in an experiment has to equal the amount of weight you end up with in an experiment. No matter what you do to them, they will balance. Now, why is that important? Because if bits of your experiment don't just magically disappear, that means you can accurately weigh what everything is breaking down into. So if you're missing some weight in your experiment, you know you did something wrong. Because what you end up with in your experiment has to equal exactly what you started off with in your experiment, because you can neither create nor destroy matter. As Lavoisier grandly announced, one may take it for granted that in every reaction there is an equal quantity of matter before the operation and after the operation. How did he figure this out? Well, he did an experiment that would look something like this. He would take some of the chemical that he was working with, say in this case, an ounce of baking soda. And then he wanted to check the reaction when he added an acid to it. So he would get some vinegar from his wife's cupboard. But not the really good stuff, Like the aged balsamic vinegar that she got as a Christmas present. No, no. Just some inexpensive white vinegar. That'll do. And then he would put on his safety glasses so he didn't get any of the stuff in his eyes, right? So he puts it on his really sensitive scales that Lavoisier spent a lot of time and money to develop, and he weighs them together. Okay, so according to this, my electronic scale, I'm starting off with 6 ounces together. Then Lavoisier mixes them together for the reaction. It's foaming all over and releasing the gas and ultimately turning the baking soda vinegar mixture into just a watery-like substance. Wow, Lavoisier would say, I started off with 6 ounces of stuff, now I have only 5 ounces of stuff left. Where'd all the stuff go? Oh, that's right, it just boiled off and disappeared. Or did it really disappear? Lavoisier thought, what would happen if I enclosed the entire experiment inside a sealed glass flask? Would the chemical weight change? Would the stuff really disappear? So, being a really rich guy, he ordered custom sealed flasks from his local glassblower so he could keep everything under tight control. It's like making a little miniature world, like being God over the beaker. That's what Lavoisier would do, but since I'm not Lavoisier, I'll use a bottle and a balloon instead. We will put the vinegar in the bottle and the baking soda inside the balloon. It'll be very much like Lavoisier's sealed glass flask. Now we weigh it up and it weighs exactly 6 ounces. Now we dump in the soda like this and wait. Look, even though the soda and vinegar were changed into something totally different, it weighs exactly the same as when we started, 6 ounces. So the chemicals changed, but nothing disappeared. It's all still right here in the bottle and the balloon, just like in Lavoisier's flask. Experiments like this, plus a few thousand others, told Lavoisier that all matter is conserved, and so appropriately he called this law the conservation of matter. Not too technical really, kind of obvious. That's probably what you would have called it. In fact, it was this conservation of matter plus Lavoisier's very accurate scales that allowed him to ultimately disprove the old phlogiston theory. Combustion needs fuel, the wax, and heat, which is the flame, and a gas inside the jar which Lavoisier named oxygen. He proved that the candle goes out not because it gives off phlogiston and saturates the air, but because the oxygen in the jar has been used up. No oxygen, no flame, yet the net weight of the entire experiment remains the same. By the way, the reason the liquid rises in the glass is because the candle flame quickly heats the air inside the bottle, just like in our bottle and quarter experiment, and this hot air expands. Some of the expanding air escapes out from underneath the jar, and you might see some bubbles. When the flame goes out, the air in the jar immediately cools down, and the cooler air contracts. This contraction of the air makes a partial vacuum, pulling the water up into the jar. The hotter the candle flame, the hotter the air gets inside, and the further the water will rise when it cools and makes the vacuum. This conservation of matter gave chemists confidence that half of their experiment wouldn't magically disappear for inexplicable, mysterious, alchemist-type reasons. All changes in chemicals were merely reactions between the chemicals. The weights never changed. Plus, this conservation of matter gave you greater control in breaking down substances so you could more accurately isolate them. Like Boyle said, nature follows the rules. At the same time, a contemporary French chemist, Joseph Proust, determined that elements combined in predictable proportions every time. Like lead and sulfur would always combine 6.5 parts of lead to just 1 part of sulfur. And ammonia was composed of 7 parts of nitrogen to 1.5 parts of hydrogen. It didn't matter if you had 1 ounce or 1 ton. It was always 7 parts of nitrogen to 1.5 parts hydrogen every time. Very predictable. In fact, they combined with such predictable, such definite proportions that Proust called this the law of definite proportions. Not too technical, kind of obvious really. That's probably what you would have called it. This law enabled scientists to figure out exactly how much of each element was in each substance. In Lavoisier's time, chemistry took a huge leap forward. Boyle and Lavoisier were to chemistry what Isaac Newton was to physics. And besides being an amazing chemist, Lavoisier was also the chairman of the Bank of France, the head administrator of a private tax collection company, and an influential member on several political councils. Positions which would greatly influence his future because, unfortunately, when the French Revolution broke out, Lavoisier's position made him a target. He was betrayed and declared a traitor. At the age of 50, Lavoisier was arrested, tried, convicted, and executed. All in a few hours. At his trial, the judge declared, "The Republic needs neither scientists nor chemists," which of course was not true and apparently did not accurately represent the beliefs of the French government. A year and a half after his death, the French government stated that Lavoisier had been falsely accused and declared him innocent. Yes, it was a little late, but at least his name was exonerated. In fact, several statues of Lavoisier are prominently displayed in Paris, France. Around this same time, the first glass of carbonated soda water was invented by an English chemist and minister named Dr. Joseph Priestley. A contemporary of Lavoisier, Priestley was a scientist, but Priestley himself said he was first and foremost a religious minister and a political activist. His writings made him known worldwide, but in spite of his popularity, Priestley managed to alienate people on just about every issue. As a scientist, he defended the phlogiston theory to his dying day, and he resisted the new science ideas of Boyle and Lavoisier. As a minister, he managed to alienate most Christians by teaching that the Bible was a series of made-up stories and not real history. And as a political activist, he supported the French Revolution, which aroused even further suspicion of him by the public and the government. Eventually, a drunken mob of political dissenters burned down his house and his laboratory, and he moved to the United States, where he actually found many followers and friends in America, including Benjamin Franklin and especially Thomas Jefferson, who often read Priestley's popular books and wrote many glowing letters of approval to him. As a minister, he co-founded the Unitarian Church. As a scientist, he discovered oxygen, nitrous oxide, and other important gases, and his writings on electricity and chemistry influenced others for over a century. plus he invented carbonated beverages. Though he was wrong about many of his scientific theories, and he was wrong about the historical accuracy of the scriptures, Priestley was in fact a scientific giant on our journey to the periodic table of the elements. Some scientists are so brilliant and so unique and so eccentric that you simply have to mention them. Priestley was one of them, and another was Henry Cavendish. At the age of 18, Cavendish left Cambridge University because at the time, students had to declare that they were Christians, and well, Cavendish simply could see no logical connection to that. Yet 10 years later, after leaving Cambridge, not having any kind of a degree and never having written a single scientific paper, he was inexplicably admitted into the Royal Society of Science. No one before or since has ever been admitted into the Academy without a degree. He was a tall man with a thin, squeaky voice and tended to look like a poor man, wearing rather old, shabby clothes and always the same worn-out hat. He was extremely reclusive. Then again, suddenly, Henry Cavendish became fabulously wealthy overnight, probably the inheritance from a local relative. As a result, he was called the most learned of the rich and the richest of the learned. He made nearly every meeting at the Royal Society, though he hardly ever spoke to anyone there. If your conversation truly engaged Henry Cavendish, you might be found worthy of a mumbled reply. In fact, one of his contemporaries, Lord Brougham, said of Henry Cavendish, "Cavendish probably uttered fewer words in the course of his life than any man who lived 80 years. At his home, he built separate staircases for his housekeeper so they would never cross paths. His dinner was ordered by placing a note on the hall table. It usually read, 'leg of mutton.' He explored astronomy, optics, electricity, geology, and pure mathematics. Sometimes he would sit and stare at the moon for hours. Truly eccentric, yet brilliant. In fact, Cavendish was the first person to understand that water was in fact made of two different gases. But his last great experiment was done in a laboratory that he built in his garden. There, Cavendish built an amazing apparatus using weights and torsion bars, which accurately determined the weight of the Earth. And he was correct to within 1%. For years afterwards, his neighbors would point out the building and tell their children that that was the place where the world was weighed. Priestley and Cavendish were two luminaries who stood out during this period. Yet, as brilliant as they were, it is Boyle and Lavoisier who are considered the co-founders of modern chemistry. At the same time that Thomas Jefferson was President of the United States and the Lewis and Clark expedition was underway and Napoleon was busy conquering Europe, an English Quaker named John Dalton was pursuing his lifelong fascination with the weather. Meteorology was his love and ambition. It seemed to be his purpose in life. In fact, he never did marry, and he kept only a few close friends. But he always carried around his weather measuring apparatus with him wherever he went, even on vacations. And he always took his journal to write down weather observations. Tens of thousands of meteorological observations meticulously written down in his journal throughout his lifetime. Dalton started his own tutoring school at the age of 12, using a copy of Lavoisier's The Elements of Chemistry as his textbook. He was almost entirely self-educated, learning most of his early mathematics and science by teaching others. He was quite brilliant. He determined that the aurora borealis was actually a magnetic phenomenon, which it is. He explained the mechanics of dew condensation in the morning, and he invented an accurate table of vapor pressures of water at various temperatures. He had already published several papers on his meticulous meteorological observations and even conducted groundbreaking research on the nature and cause of color blindness, because Dalton himself was actually quite colorblind, a fact he discovered himself when, one day, he purchased what he thought was a pair of dark-colored stockings for his conservative Christian Quaker mother, since Quakers did not wear bright-colored clothing. She was a bit taken back when she opened the package and found John's present, a pair of brilliant scarlet red stockings inside. Dalton couldn't see the difference, and so he began to investigate. And through his work, he was actually the first person to describe red-green color blindness, which he had, and is even sometimes known as Daltonism. So Dalton was a meteorologist, and a colorblind meteorologist at that. But it was his love for the weather and the study of the physical properties of the atmosphere and gases that the idea of atoms rose up in his mind. At about the age of 35, Dalton, like Robert Boyle, was convinced that Democritus's idea of uncuttable atoms was correct. But this time it was not just a philosophical theory. This time the atomic idea would have some real, tangible chemical measurements to back it up. Now, Dalton understood that every element was made up of different stuff: carbon, oxygen, silver. And so that meant that each of their individual atoms was also different. But in what way? What was fundamentally different about every atom? And it was here that Dalton made a guess. He guessed that what made each atom different was their weights. So that every hydrogen atom weighed the same as every other hydrogen atom, but it weighed something different than every oxygen atom and something different than every silver atom. It may be ridiculously, almost infinitesimally small, but it has to be something, because if you get enough of them together, you get a chunk of it, which you can weigh on scales. So, each atom weighs something different. That was Dalton's first guess. Now, not every scientist was enthusiastic about Dalton's ideas. Many of them didn't even believe that atoms existed, and many others thought the whole idea was completely irrelevant. After all, if atoms were as small as Dalton was suggesting, then you certainly couldn't experiment on them, and you certainly couldn't weigh them, which is a good point. Weigh an atom. It's not like you could just take an atom and throw it on the scales. In fact, we now believe that atoms are so small that 50 million would fit across this M&M. I mean, that is really unimaginably small. Or, to see it another way, if an atom were the size of this M&M, you would be over 10,000 miles tall. So if they are so ridiculously small, how did he weigh an atom? Well, the answer is indirectly. In fact, a lot of science is done indirectly because you're either dealing with things that are way too big, like the universe, or way too small, like an atom. Here is an example of an indirect way of doing science. In this case, how to demonstrate that some gases are heavier than other gases without actually weighing them on a scale. Baking soda and vinegar combine in a chemical reaction to produce a gas, carbon dioxide in fact. Now, a flame will not burn in carbon dioxide gas. So we light a little candle in a jar. In another jar, you mix, say, a tablespoon of baking soda and a glug of vinegar. Wait until the reaction slows and produces the carbon dioxide. Is it heavier or lighter than the surrounding air? You can't see the carbon dioxide gas, but we'll pour it into our first glass as if it were there. Now, take that glass and pour it over the candle. And yes, it extinguishes the flame. This gas is obviously heavier than the gas that was in the glass surrounding the candle. That is a typical example of the indirect means of knowing something exists even if you can't see it. Now, when it comes to actually weighing an atom, we will skip some of the minute details for sanity's sake. But basically, this is how Dalton did it. He knew through his own experiments and the experiments of others that when you break water down to its basic elements, you always get 1 part of hydrogen by weight and 8 parts of oxygen by weight. The law of definite proportions. Every time a chemist would separate, say, 9 pounds of pure water and collect the gases, they would get 8 pounds of oxygen gas and 1 pound of hydrogen gas. The same proportions every time. So that meant that water has almost 8 times more oxygen than hydrogen. Based on this information, Dalton made another guess. He guessed that since water always divides 1 part hydrogen to 8 parts oxygen, that meant that water was made up of 1 very light atom of hydrogen and 1 very heavy atom of oxygen, which weighs in fact 8 times the hydrogen atom. And so he assigned to hydrogen the weight of 1. 1 what? Well, not 1 of anything really. Since the scale was so small, Dalton basically invented a brand new scale that weighed all of the elements against hydrogen, the lightest element, which was now given the atomic weight of 1. And everything was weighed compared to that. So, 1 atom unit is hydrogen. And since oxygen separates out 8 to 1, he gave oxygen the atomic weight of 8. 8 atom units. And that really is the beginning of what we call atom theory, atomic theory, the theory of atoms, that they exist and that they actually weigh something, and that weight is responsible for why all the atoms and all the elements are different from one another. Dalton published his work in a book called A New System of Chemical Philosophy. In it, Dalton developed an interesting set of symbols that represented each element: hydrogen, nitrogen, carbon, and so on. Dalton thought that atoms were like solid billiard balls, so he drew a circle representing the atom with a little symbol in it so you could tell them apart. Plus, he had his new list of the elements with their brand new weights, all compared to hydrogen. Hydrogen was 1, of course. Nitrogen was 14, meaning that 1 nitrogen atom weighed the same as 14 hydrogen atoms. And carbon was atomic weight of 12. Gold was a whopping 197, meaning that 1 atom of gold weighed the same as 197 atoms of hydrogen. What's really great about this idea is that Dalton provided a link between the level that we can see to the microscopic level that we can't see. So, if we know that water is always dividing 1 part of hydrogen to 8 parts of oxygen, then that probably means at the atomic level what we have is 1 light hydrogen atom that's combining with an oxygen atom that is obviously then 8 times heavier. Dalton made solid wooden spheres like these as models of what the atom looked like, an idea that received assistance years earlier from Isaac Newton when he wrote that God in the beginning formed matter in solid, massy, hard, impenetrable, movable particles. Now, many thought that Dalton was on the right track, but not everyone was convinced, of course. In fact, one openly hostile critic said, "What are atoms? I know what atoms are. Atoms are round bits of wood invented by Mr. John Dalton." It would be nearly 50 years before Dalton's ideas were universally accepted. Actually, most of his critics simply died out.
which is the way it usually happens. So, if you're having a hard time getting your mind around the idea that these nearly invisible particles even exist, don't feel too badly, because a lot of very smart people have wrestled with it also. Actually, Dalton didn't get everything right, and there was a lot of work to be done. For example, atoms are almost never found wandering off by themselves, but they are almost always bonded together with other atoms. And what makes them stick together? Well, Dalton thought that atoms had literal hooks on them. By experimenting with how many they combine with, he thought that hydrogen had only one hook, but oxygen had two hooks, forming either water or hydrogen peroxide, for example. Chemists refer to this bonding characteristic by various terms. Sometimes they call it the atom's bonding power, or its chemical affinity, or its combining power, or combining strength. Eventually they settled on the word valence, which they got from the word valor, since valor means strength. Lithium has a strength, a valor, a valence of 1. Beryllium has a valence of 2. Boron has a valor of 3. And carbon has a valence strength of 4, and so on. Essentially, the valence of an atom was just how many hydrogen atoms it would hook up with. And Dalton thought that the valence ability came from the number of hooks on each atom, giving it more or less ability to hook up with other atoms. Well, he got the hooks wrong, but he was close. Also, Dalton got the weight of oxygen wrong. He thought that water was made up of 1 hydrogen atom and 1 oxygen atom, which weighed 8 times more than the hydrogen atom. In reality, water has 2 hydrogen atoms for every 1 oxygen atom, which then makes oxygen twice as heavy as Dalton thought. Not 8 times heavier than 1 hydrogen, but 16 times heavier than 1 hydrogen atom. You see, Dalton thought that atoms generally combined 1 to 1. Why? He guessed, again. He guessed that that was the simplest way that nature would do things. He even called it the law of greatest simplicity. And it's true a lot of the times, and it allowed atomic theory to go forward. But he didn't guess wrong on everything, and he didn't just go around guessing either. He was actually one of the most brilliant experimental scientists of the 1800s. If Boyle and Lavoisier started the chemical revolution, it was Dalton that put it on a firm foundation. Lavoisier didn't even believe in atoms, but Dalton did. The Swedish chemist Jans Berzelius said, "If one takes away from John Dalton everything but his atomic idea, that alone will still make his name immortal." Financially almost the opposite of Lavoisier, Dalton was the son of a fairly poor weaver, born in a remote English village, and was almost completely self-educated. He enjoyed taking his leisure at this little pub, the Dog and Partridge. Dalton led a modest lifestyle, although he received many honors later in life. He died in 1844 in Manchester, England, soon after noting the weather conditions for the day in his journal. Dalton was a man beloved by his whole town. Manchester, England buried John with kingly honors, and incredibly, more than 40,000 people marched in the funeral procession for this simple but extraordinary Christian Quaker man who proved that all matter is made of tiny particles called atoms.